Hey everybody, picking up on our notes for 1.2, calling this 1.2 part 2 or letter B. We're going to talk about half-life. So some things about half-life, including how we can use it to calculate some things. Starting out with the definition here. So half-life is the amount of time that is required for 1/2 of the nuclides of an isotope to decay. And I know you guys have seen that word before. It was in your band of stability lab. Nuclide just refers to the nucleus of a radioactive isotope. So if something is radioactive and you're specifically talking about the nucleus, you can call it the nuclide or anuclide. And we know that because it's radioactive, it's unstable. So half-life, it's an amount of time, so seconds, years, days, hours, milliseconds, for half of those nuclides to decay into a more stable product. If we were to look at a graph form of this, it would look something like this, where up along the top there you have red atoms representing isotopes that are radioactive. And then after one half-life down here, we can see that half of those have turned gray, so the daughter isotope, which is no longer radioactive and stable. After one additional half-life, half of those have turned gray. And what I like about the way they show it up here on the top is that it's very sporadic and random. It's not like the top half turn gray or the bottom half turn gray. It's just very random, but it's at a given interval. We know that half of them will decay. It's that half-life that we can play around with a little bit more because each isotope has its own unique half-life time. So for example, you guys can see this very first one, polonium-214, it only takes 163.7 microseconds for that half-life to occur. So half of those atoms that are radioactive, those nuclei will decay, half of them in 163.7 microseconds. So it's really unstable. Its decay is going to happen quickly, it's going to release radiation very quickly, but then it's also going to become stable very quickly. You can contrast that to uranium-238, which it's going to take 4.46 trillion years for that to happen. So it is decaying, it is unstable, but it's not as motivated to decay as quickly. It's kind of like, we'll get there when we get there. So it's going to take 4.5 trillion years for that same amount of decay to occur. So again, it's still emitting radiation, it's doing it more slowly, but also it's taking a lot longer to get stable. And then there's some other ones on there that are just kind of common and good to know. Radon, we've talked about a lot. Strontium-90 is a product of nuclear waste, is a component of nuclear waste. Strontium a lot of times gets mistaken for calcium by our body because it's in the same family. So if it gets mistaken for calcium, it can get into our bones and be radioactive for 29 years, a half-life. So it can stick around for a nice long time being radioactive and cause things like bone cancer. Carbon-14 is used for carbon dating, especially things that are really old. And then cobalt-60 is going to be used in things like medical imaging. So these things we can all look up. We can Google them. You don't need to have half-lives memorized. I just wanted to show you that half-lives can range from very short to very long, and each isotope is going to have its own unique half-life length. Okay, so let's jump into problems. These first types of problems that are going to ask how much of something is left that's radioactive. So you're looking for this, how much is left or how many are left over after a certain amount of time. We're going to call these type A problems. So type A problems we're always going to tackle the same way. So in this case, how much of a 20.00 gram sample of radioactive strontium, and that should say strontium-90, will be left after 145 years. So step 1 is to determine the number of half-lives that have passed. We're going to symbolize half-life with the number of half-lives by the lowercase letter n. And to do that, we just divide the amount of time that has gone by the length of one half-life. So the amount of time that has gone by in this particular problem is 145 years. So we can say n equals 145 years, and we're going to divide that by the half-life of strontium-90, which we can look up. So if we Google the half-life of strontium-90, we get 28.8 years. Oops. Okay, so if I look at those two, I divide 145 by 28.8, I get 5.03 half-lives, or lowercase n. I'm using 3 sig figs because both of my values there had 3 sig figs, and I'm dividing. Step 2, I would take that number of half-lives, and determine what fraction then, based on that number of half-lives, have decayed. And to do that, I'm going to use 1/2 to the n power. So in other words, I'm saying, how many times do I have to divide my sample in half? If 5.03 half-lives have gone by, I would need to divide it in half 5.03 times. Now, if I had a nice round number like 5, I could easily, just in my head, divide 20 in half 5 times. But 5.03 means it's a little bit more than 5 half-lives, so that's where this equation comes in handy. So I'm going to take 1/2 and I'm going to raise it to the 5.03 power. And if I do that, I'm going to get 0.0306. Okay, so that's like out of 1. So if you think about if the amount of nuclei that are radioactive at the start was equal to 1, 0.0306 would be the amount out of 1 that is still radioactive. If you wanted to think percent-wise, you just multiply that by 100. So you'd move the decimal, so it'd be 3.06%. But we don't really need to do that because we're going to use this number to multiply by in our next step, so we can just leave it as that decimal form. So out of 1, 0.0306 is the fractional amount that is remaining after 5.03 half-lives. Okay, step 3, we're just going to take that fractional amount remaining and we're going to multiply it by the original mass of radioactive material. So that capital N, this is what we're actually looking for, N, which is the amount that is still radioactive. And N0 is the original mass, or sometimes it's not a mass, sometimes it's just an amount, like a number of atoms or something like that. Eventually we're going to talk about moles, so it might be the moles of radioactive material. It's just an amount. So we're going to multiply those two things together to get our answer. So in this case, the amount that's still radioactive is equal to that 0.0306 we just got from the last step. And we're going to multiply that. In this case, I don't have the question right in front of me, but hopefully you wrote it down. The original mass of strontium-90 that was radioactive was 20 grams. So if I multiply those two together, then I'm going to get my answer, which is 0.612 grams. And again, I'm using 3 sig figs because I have 3 here and 4 here. All right, now you're going to try some type A's. Good luck.